welcome to this event in collaboration with a bunch of people, especially Vulpine Labs, and in collaboration with MetaGen and Transhumanists in VR. Yeah, so thank you everyone for coming. I think it's gonna be very interesting stuff that they're gonna be discussing, and don't hesitate to ask questions after the talk and hang out and have fun. So yeah, I don't know if Atha wants to say anything, or I'll just hang it to Alynna.
You want to say anything?
You can go right ahead.
Alright,
Okay.
grab
There
this
you go.
now. Testing. Okay, I think I've had enough tests. Hi, my name is Alynna. Usually go by Alynna Trypnotk. Well, actual pronunciation. Okay, screw it. But you can call me Alynna Kelly, that's my legal name. I'm with Vulpine Labs, currently the Chief Science Officer. And right now, what I want to present today has to do with implementing a DNA processor using extensions in the RISC-V architecture. That's my current project in Vulpine Labs, and on top of that, we are going to go ahead and talk about the architecture a little bit and how it's going to allow us to achieve our goals.
All
right.
Like to point out that this
Speak.
is not...
Come up here if you're going to talk.
Yeah, let me
Come.
go up there.
Yeah, you might as well be up here with me so that you could talk.
All right, so
Better.
yeah, so the gene editing approach to morphological freedom is our passion at Vulpine Labs, and it's not an easy thing to develop, but it's going to be worth it for the reward. And we believe that the devices that you use, the tools that you use, are really essentially got to have the right tools for the job. So Alynna has been working on a fascinating approach to this, using RISC-V to actually power the processing of DNA. We're hoping that by doing this we can actually take what would be something that would need a whole data center of workstations or something, make it just that little bit more manageable.
Sorry, I was having a glitch out moment.
Yeah, fortunately we'll be testing things a lot before any gene editing systems are allowed near people, so that glitch out modes don't become too big a problem. We are going to be taking that gene editing approach, and we want to be bringing down the total cost. We want to make it simpler and easier to understand how to use the systems and devices, make it open source, and make the system trustworthy. So between those things and making the gene edits available to everybody and having it all work seamlessly together, these systems need to be developed in a manner that overtakes current technological development. So we'll come back to these slides perhaps if we have more time at the end, but because we've taken a while to set up, let's get straight to the point here. The GUESS is our gene editing software suite that we are working on. It stands for the GUESS Universal Editing Suite and SDK. It's a highly detailed digital twin model with interfaces to handle and automate adjustments on anything from your genes to the genes. And it can, when fully developed, use genetic data from you as input and combine that with a vast collection of knowledge on genetics of all relevant kinds to enable you to apply arbitrary changes to that model of yourself, and then using that same system to design in silico testable gene editing vectors that you can then export to an actual biological gene editing vector that you can apply to your body. So the Geneticiser will be designed to read your DNA as the input and provide it to the GUESS, and to write the gene editing vectors that are provided to it by the GUESS as an output. So it will be essentially the printer and scanner of genetics in general. But there are numerous challenges to overcome, including, of course, internet connection issues, if we want it to be as easy to use, versatile and useful in the field as we envision. So some of these challenges can be met by classical methods of designing and coding and computing. For those that aren't, we can try quantum computing and AI. And I think it's important as a first step to get used to using analog architectures, ASICs and such, and RISC-V provides a great architecture for that, and it gives us something that we can start to integrate with our hardware devices that we're developing for this. So here comes AI, because everyone's sort of been talking about AI recently and it's become the big zeitgeist. You know that AI is taking over a lot of different fields and people are saying, oh, you're not going to have a job anymore because AI is going to do it for you. Where we're really interested in it is what it can do to understand and process the complicated nature of a gene editing system, and to help us with coding it, to help us with actually making certain decisions and certain processes work better in a system like this. We already had a few ideas for AI well before the likes of ChatGPT came out for how we could integrate it into the GUESS. So We were looking at things like, could AI be used to help you with nutrition, making sure that any gene edits that you're going to apply have sufficient supplies to actually work. We were looking at how could AI help with understanding how your model of your body looks, whether it is accurate, whether it is going to be something that falls in the uncanny valley or not, which is definitely a very subjective matter, so it would be very interesting to see what AI thinks of that and whether we can come up with a standard for it or not. And so it's a bunch of different aspects of the system that we're looking at applying AI to. And when we came to the notion of using RISC-V, we were looking specifically at how do you actually streamline the molecular side of things, dealing with the DNA, dealing with the proteins and such. So that's where we were getting to. And AI previously was dealing with things like Markov models, relatively straightforward and simple. A few people would say that some of the recent developments in AI are somewhat more advanced than that, as this meme might imply, but at the end of the day, it is still possible to understand what's going on in an AI. It just needs to be coded and designed such that it does actually show you it's working out. So that's something that we're sort of keeping very much in mind. The big diagram that we have up on the screen there, that ridiculous code diagram that's created, is of all of the different submodules, all of the little pieces of software that go together to make the guest system and how they connect to each other. So it's not very practical to actually use that diagram because it takes forever to load, but it does at least give a nice visual representation of what we're dealing with. We have other ways of tracking what connects to what, but this was fun to make as a visualization of it all. So you can see it's complicated. It's basically the scale of an operating system. And we needed to develop the software, really, but we needed to figure out what's going to come first anyway. The AI would help to cover the initial outlay on revenue gaps on large projects and speed up incubation, but we also need to have some kind of finance, some kind of income to cover things in the first place, like anyone does in this world. But we're making progress gradually anyway. It would just be lovely if we can have a little more help with that, but, you know, get there in the end. So, sometimes we decided we have to take some risks, and Alynna, you know a thing or two about risks. Here you go.
Yes. Alright, so I guess now I got to my part of the presentation. I kind of felt that the introduction to guest was required, because if I don't have that first, then nothing else is really going to make sense. So, first of all, I think it is pretty obvious why I chose RISC-V as a basis to basically create a DNA processor and accelerator. We want to have architecture that's open as possible. Number one, if we go to ARM or Intel or the ARM consortium or whichever and say we want to add extensions for DNA processing to that, they're going to just basically say, heck no, what's the use of that? And somebody else who is working on a 128-core CPU went to the ARM Association and asked the very same thing about adding extensions for this, their particular needs, and they basically just didn't even respond to it. They don't allow you to extend the architecture. A RISC-V is entirely different. I did join the RISC-V association so that I could keep on top of what they are doing, and RISC-V already has places for you to put extensions to the instruction set. That's what we need to do here, is extend the instruction set, because we can have general computing and DNA compute all on the same die. So you're not passing this data across a slower bus to something else like a GPU. I'll talk about GPUs in a moment. The other thing is RISC-V is simple enough to implement something like RISC-V 64GC extension that gives you the basics, and then to put the XGuess stuff right after it, and that's kind of elegant. And on top of that, you can use a general, sitting on my desk, I have a Nexus 4 DDR, which is an FPGA with lots of logic elements, to actually create the processor and place it on there and have us be able to run it and simulate it Well, at that point, you're not really simulating, you're just prototyping it on an FPGA where you are able to basically have a initial unit running on it. So, what does that mean for the Geneticiser? First of all, once we have something working on an FPGA that can do something very important that I'm going to explain later why this is important, once we have it on an FPGA, we can turn it into an ASIC, make it very, very cheap for us to replicate, make it very cheap for others to replicate. It's going to be an open platform. So if you want to build your own board, or you want to start a company that builds the board and gets it out there, then you will be able to do it. You'll be able to go on to GitHub, where we're building the architecture, download the VHDL and Verilog. I'm actually using both, and synthesize it yourself. How this works, actually I'm going to go over it right now since we're pretty much there, the instruction set. How this works is that you got the general 16 to 32 registers of RISC-V that you could use for general computing, but the XGuess extension to the architecture actually sees those registers as groups of codons and amino acids. Basically, about 6 bits are for the codon types, and another 6 bits at the end. Actually, I think that's 7 bits are associated with an amino acid, and then there's a few bits to say if there was an error, if the result was unviable, and all of these instructions end up not being a whole bunch of code. They end up being a few instructions. Just like addition would be, just like multiplication on the processor, shifting bits. All of these become instructions. Now, these instructions take longer, 10 to 100 cycles, but when you compare that to the software code that may take like 10 to 20,000 cycles to perform the operation, then you can see that it's going to be a huge speed up in being able to do it. And on top of that, it almost becomes inappropriate to call it the guess. And I'm hoping that this architecture gets to the point where it actually will say from this DNA pattern to that DNA pattern without error and without any sort of, if there is an error, it will be flagged, say it's unviable, and then you could calculate the result to create a completely viable change from one organism to another. Alright, we could do the next slide. I explained that. Extensions to operate on registers. They're building a 128-core RISC-V, and since that's going to be open source, we could just pull their stuff in to synthesize that processor if we need 128 cores of these. I watched that video. It's pretty great. As I explained, the DNA data types map as registers, and then when you're not using those instructions, they're just regular registers. So you could use software that operates on it and then immediately go to an instruction that accelerates that because it already knows what to do. What we're basically going to do is take a bunch of information and work with other biologists and geneticists to say, find out one group of codons and how that would work with an amino acid, how it would change it. We put that in VHDL and synthesize that process into hardware instructions, effectively creating a DPU, a DNA processor, that operates on both DNA and regular instructions. So if you need to do some kind of addition or something, you could do that, go right back to DNA acceleration. It's all in the process. So you don't even have to change modes or anything. There's where we're starting it. As you could see that I have GitLab. That's our own GitLab, actually. But I'm starting with the RIFT2 core because it's small and it can go straight into a Nexus 4 DDR FPGA. Then we want to import GPT for all as a software component because we're going to be gutting it and then training it on DNA. Basically, instead of doing a language model, we want to teach it about all the things like cats, foxes, humans, and just give it all kinds of data about all of these creatures. And then, once it has all that data, it can then be told, we have this, we have a human, there's its DNA. There's their DNA, he, she. Let's say it's my DNA. My DNA is the input. The output is this fairy box, because that's me. The output is this, these are the changes that was required to create the creature I want to be. Now, use our accelerated instructions, which it already knows, to get from here to there. And then it will synthesize the instructions required to do it. And then it will execute those instructions and show which proteins need to fold, what this change. It will basically give a change log of every single DNA change and protein fold and other nucleotide changes that are required to bring an organism from here to there. All of this stuff is going to be released as open source. You will probably either need to be able to buy the hardware or synthesize the hardware on an FPGA yourself. You'll have a bunch of options. We're going to make as many options as possible to make sure that, one, because we're using RISC-V, it will never be owned by a single company. Nobody's going to be able to lock it down. Once it's out there, it's basically the same thing as anything else on the internet. It's out there. Nobody can stop it. The second part is that, like I said, with XGuess, we have the freedom just to dump the VHDL someplace where it can never be taken down, and anybody can get at it. Neural processing units are planned to be things that you can attach to things that you can attach to the bus to be able to accelerate things even more. They won't necessarily be necessary, and you'll be able to use proprietary hardware for that, like you'll be able to use any kind of GPU to act as an NPU there. However, it will go through an API that abstracts it, so that any other device, including free devices, if they do something to that architecture that makes it impossible to run our code because they have a moral problem with it or something, you just replace the device with something else. Something like if AMD has a problem with it, you put in an NVIDIA. Put in an NVIDIA Jetson in there, or use one of the open source NPUs that are out there. We're able to use a closed source interface as long as we write the API for it. We are going to be using GPT for all. At least that's my current plan right now. Something better might come out. AI is advancing so fast right now that I'm basically ready for the singularity any day now. But better things might come out. So, okay, you need to be this part.
So, yeah, after all that, we could use some help. We are a public benefit corporation. We're volunteering a lot of time to get this thing going, and all the trials and tribulations of setting up a presentation for VRChat mean that we're probably coming across a little more discombobulated than we usually do. But that aside, we have been making a lot of progress with this system, and it would be amazing how much more progress we could make when we can actually pay developers, and when we can really afford to cover the hardware that we need to do this justice and the time and effort that it takes properly. So if you know anybody who knows anybody who has some kind of spare cash floating around that they don't know what to do with, then please point them to us and our links at the bottom of this screen. That's patreon.com, Vulpine Designs, and investors at vulpinedesigns.com.
If you know VHDL or Verilog, we're going to need people with that kind of knowledge pretty soon. That's the big thing right now. Also, if you know about protein folding and can help me, I mean, I could do VHDL and Verilog all day. but I'm not a geneticist. I don't know exactly what process A goes to B, but what I can do is once I'm told that, then we can turn it into an instruction that can be accelerated in RISC in VHDL.
Yep, we can always use more scientifically minded folks. I mean, I know a fair bit about how this system works myself. I mean, I designed most of it. I had some help, though, from our good colleague, Avali, and it's really coming together quite well. And now we've actually rejigged how we think about things, how we put together our processes and our systems, and so that's what this symbol behind me is about. We've actually joined an organisation that we refer to here as Put Together, and it's basically meant to be a force for good and positivity. Gist of it, it's sort of a movement with constructive progression of development of technologies and of social interaction and everything in mind. So it's really a loosely put together thing, funnily enough, but it's there to help us really get ourselves in motion as much as anything else. And freedom of form is an evolution revolution, and it's what we believe in, it's what we're developing all this for. We want to see everyone being able to become whatever they want to be, and that includes simply healthy. So if somebody just simply wants to get rid of the susceptibility to cancer or whatever, there's systems for that too. You know, it's not just about furry transformation, but furry transformation would be pretty damn cool as well, and the same tools are needed for both. So let's do this thing, because I think we're going to be able to make a lot of people very happy if we can. So I look forward to hearing from those of you who'd like to help us out. There you go.
I was just going to say that if we had our system in place right now, and COVID came around, for example, it would probably have taken days to create a perfect vaccine for it, because we could simulate the process of having a body that has it and by having a body that's resistant to it. All we would need is an example of one person who was basically naturally immune to it, and we could have created that immunity. So, I mean, yeah, there's a huge health aspect to it as well, because it will be possible to create genetic changes that make people immune to all sorts of things. Yeah. We can get rid of, we'll never get rid of the sicknesses, but we can make it so that they can't kill us. There you go.
Like Alynna was saying, when it comes to viruses, when it comes to any disease that spreads around, at the moment, the best in technology for that is basically the mRNA vaccine. That's the best that's available to the public. And mRNA vaccines are a good step forward, don't get me wrong. You know, they're very good.
It's really smart, yeah. But it is. But to be honest, it's an analog version of what we're trying to do.
In a sense, the mRNA vaccines can put in a one-time fix, but what we're looking for is an ability to constantly update ourselves, basically. So you take a look at how the immune system actually works, you read up about immunology, and it's a library of different things that the body can fight against and how it fights them. So if we can have a system like the GuessTech and Geneticiser where you can download gene editing vectors, you can download the content of them, you'll be able to literally download updates to your body to fix security holes, essentially, that let viruses in. So then, instead of a vaccine taking time to spread around the world while they're manufacturing these vaccines in all these different factories and such, if everyone had a Geneticiser, then it's just a matter of downloading it. You would download a vaccine. You absolutely would.
And additionally, it would be available for free. You would not be able to have, like, Big Pharma come in and say, it's no longer a national emergency, so now we're going to start charging for the vaccine. Like, screw that. That industry is evil. Because they're sitting there, they're capitalizing on our health. And we'd like to see a future where companies cannot capitalize on our health.
Precisely. If you take a look at Martin Shkreli, I think he exemplified the problem. And the other problem, of course, that pharmaceutical firms have, which isn't mentioned enough really, is Eroom's law, which is that things develop kind of slowly. It takes ages for them to create a new drug because it's getting more difficult to find these specific molecules that don't have side effects and to at the same time develop them in a way that avoids all the patents that already exist for drugs. And so it's actually becoming more expensive per drug each time they develop one. So Eroom's law is the opposite of Moore's law because it's becoming twice as difficult, twice as expensive over time, and taking twice as long. So we need to do something to change that paradigm completely. So the pharmaceutical industry obviously knows that, and I think that's one of the reasons they've gone to things like mRNA vaccines. But it's not enough quickly enough, really. We've got to do more to save lives.
Are we at the point where we're taking questions now?
Why not?
All right. Let's go for questions.
Oh yeah, any question?
Do you all like what you hear?
That's a yes.
I guess it's yes.
Yeah.
Yay! Yeah, hearts over there.
So I have one question, I guess, like technical skills or know-how. What's the biggest bottleneck that I think you have? I think you mentioned you know a lot about Verilog and circuit science. Atha has more knowledge on the bio side, but what would you say is the most important missing piece in terms of knowledge?
We could definitely use more people that have that knowledge. We have a couple biologists on our team. What we actually need is to be able to pay biologists and stuff, because it's hard to get people to be able to commit a lot of time to this when we can't pay them. We would really like to be an organization that can pay the people who are working for us so that they could spend 40 hours a week on it instead of like half an hour to 1 hour. As CSO, I've been trying to say, okay, let's at least spend an hour or so a week at least discussing where we want to go with this. But things are so darn slow. Once I studied the nature of RISC-V, I came up with the idea of, instead of waiting for AI to get someplace and quantum computing to get someplace where we would need it, actually the RISC-V architecture was the first thing that came along. It had the code space, the extensibility for me to say, okay, we could just VHDL what needs to be done. And that's doable with what we've got. We've been trying to get this going for about 15 years now. And the last 15 years, it's like the technology hasn't been there, and we haven't had the resources to put, I'm just going to say resources, because it's not just funds. I mean, it's people, it's access to ASICs and FPGAs so that we could actually create prototypes of the hardware. But in general, it would be easier to do this with more money. I can't really ask for it, but she can. But, I mean, honestly, we could fail at doing this, but we don't want to, and we think that we can succeed. We believe that.
Yeah, we know we can succeed. We have the designs, we have the concepts down, and we're getting them more and more detailed and refined each day, really. And it's a matter of time and money, people available to give that, that's the gist. So there's more details than we could fit into a presentation about exactly how it all works and what all the modules are and everything else. So that's the sort of stuff that you got to come to us and ask us about or find on our YouTube channel. We do have a few videos now about some of that. We already have the first of the 27 modules now that the guest is going to be constructed of. The first one is Initiator Set. The Initiator Set module is basically dealing with mRNA to protein translation. We have a demo of that already on our YouTube and in our GitLab. So if you want to try it out, let us know. I'm not sure if the version in GitLab is currently fully working, but we can quickly get it working again. The demo was obviously made when it was working. So at least there's a video there. And it shows you what we can achieve just on basically zero budget in terms of processing mRNA and proteins in a way that several universities over many years have been gradually making tools that do little pieces of it here and there. There was this piecemeal mess of bioinformatics software out there on the internet, and one or two attempts to make something a bit more joined up, but nothing on the scale of what we're trying to do with the guests. So they were not thinking big enough, really, nor were they thinking joined up enough. They were just thinking about their particular pigeonholes in science, which obviously is great if you want to make a PhD thesis, if you want to make your lab famous, your university famous for having discovered this particular protein and what it does, or whatever. But if you actually want to get to the point of something usable on the scale of the whole body, you've got to scale it up. You've got to think about joining all these ideas together. So that's what the guess is about. And I called it the guess originally because it was a bit of a slight joke to say it will take its best guess for anything that it doesn't already have the data for. It will fill in the gaps, it will extrapolate. And that's one of the things that the AI is meant to do, actually, is to help to fill in those gaps where science hasn't quite got enough info yet. And the hope is that we will have enough info at least where any such gap filling that is done is good enough that it doesn't deviate really from what's actually going to work. But that is gradually being improved on as scientists continue doing their work in various institutions around the world and contributing to the huge corpus of data that is going to be used by the guess. So over time, this is only going to get better. And if we can put money and effort now into developing our interface for this and how it processes these data, then we can contribute back to those databases that all these scientists and universities are making as well. So that's our approach.
I think bottom line is that RISC-V and the XGuess extension, it's viable. It's not pie in the sky. It's not like imaginary science or anything like that. It is utterly viable, and it can be done with technology that is out there today. You could get yourself an FPGA for $200, and you'll be able to simulate or synthesize and run the processor on your own board and see what it does. And then that could be part of a bigger system. This is step one, being able to show that the DNA is here, and now it's here, and there's nothing wrong with it. And that's one of the reasons that I wanted to go with RISC-V, get the uncertainty out of the system, and be able to run a simulation that shows that this change will create the changes that are desired in the DNA, and the person won't die in the process. Because every single codon, where there's an error, in the registers, those things are flagged with an error bit. So you can see where there might be a prion result when you're doing a bunch of folding it across. If you're trying to get from, like, have fur on your hands, all the things that are required, it would encode the process, and then when it's processed, the AI would encode the process, and then that would be handed off to the XGuess, which would then basically simulate it by its instructions to codon interpretation and the instructions that simulate the protein folding and other processes that are required to occur. And then you find out at the end if there were problems. And you find out basically you could try a different group. And you'll be able to submit all kinds of things over and over to find out which nucleotides and which amino acids will work here to get you there. And since those are going to be basic instructions in the processor, they take 8 to 10 cycles and not 100,000. So very fast, very retestable.
Thank you very much, Alynna. I think you've really accelerated our work here with this. I'm very glad that you came up with the notion of using RISC-V for this. I think it's a very good idea. So I'm sure some of you have attended Tholin's talks before as well about making open source chips. So maybe this is a friendly crowd for that.
Talk?
Yeah. Did you want to step forward, Thorinair?
What do you think about using RISC-V for this?
I'm probably the only person in this instance who has actually designed ASICs before. But yeah, RISC-V has been extremely popular with open source silicon projects. I mean, the management controller that is included in every single chip for debugging purposes is literally a RISC-V 32i processor. So yeah, there's no shortage of different innovative RISC-V projects you can find as part of the open shuttles.
I think that's one other thing that's good about RISC-V. It used to be a thing with the S360 systems made by IBM where you could go backwards and audit every single instruction that happened. That's why you could go back and audit all of those instructions. And in RISC-V, it's kind of similar, except you could sit there in hardware. You could connect up to the bus directly and basically watch your CPU executing instructions. And because of that, the debuggability is you're able to see what your instructions will do, which really helps us accelerate creating new instructions, because when we get right down to it, XGuess is all about creating new instructions that help with processing DNA. Here you go back again. Let me actually get up. There we go. If you have anything more. That's a beautiful avatar. I like it. But man, is that cute.
Alright, so anyone else want to ask any questions? We're open.
Little kitty?
Oh, hi. You want the mic?
I'm good, thank you.
Alright, I think the kid is there as a camera person. Okay, so... Yeah, anyone else? Are we all good? Alright. Thank you all for coming.
Back there, Saphira was waving her paw.
Ah, okay, I didn't see that.
Do you want to come up here, Saphira?
Alright, can you hear me okay? So, my question is, what is the application with this? Like, where are you trying to go with this? So my question is, where is your goal with this? Are you planning on taking this into the pharmaceutical realm to apply with possible treatments like vaccines? Or are you trying to take this into the more public sector with giving people more access with their health information? Or are you trying to put this into the pharmaceutical field with development with model software? So where's the goal with this?
The goal is all of the above in some respects.
Yeah, that's what I was going to say.
Yeah, we're looking at basically changing the paradigm of how healthcare is done. So it's not just about develop the best spanner to throw at the machine and hope you hit the right nut anymore, because that's essentially what drugs are. Instead, it's about looking at the code that our bodies use to assemble themselves in the first place, the DNA, and how do we change that code so that the bodies assemble themselves better, so that they basically build their own corrections as we want them to do, whether those are corrections for healthcare purposes or for cosmetic purposes, etc. We're agnostic to that with this system because it's the same system needed for both. So really it's going to have uses in so many different fields and so many different ways that to try to put us in a pigeonhole and say, oh, they're a pharmaceutical startup or they're a cosmetic sort of gene edit startup, that would really defeat the point.
Microphone, please.
Yep.
Thank you. The thing is, we are developing a system that basically takes the impetus of healthcare away from big pharmaceuticals that are basically charging us all sorts of money. It's almost like blackmail. It's almost like, well, what is your health worth to you? But if we had systems that basically said, okay, this is the genes that make you susceptible to X, this is how you become immune to X, and then we had a system, the AI part, creating the code to get from A to B, and then the XGuess running that simulation and basically saying these are the steps required to get your body from A to B, and then the last step is actual application of that, and then basically health becomes a free digital resource.
Essentially, we're taking the problems of biochemistry, of medicine, healthcare, the body, and making them into software problems instead of such a difficult problem to solve as they were before, with having to have these molecules that are put into pills or injections or whatever and shipped around the world and in very difficult to control conditions or whatever, with specialist pharmacists and so forth having to issue them in a specific way. Instead, what we're saying is it should be as straightforward, potentially, to produce a gene editing vector for yourself that rewrites your genetic code as it is to 3D print a model, but there would obviously need to be some peer-to-peer checks put in place. There would need to be some ways to ensure that these are verified as functioning properly, so that we're not just saying, hey, stick anything in yourself that might cause you problems. So there will be ways of making sure that this is done the right way. And yeah, go on.
The thing is, I think the FDA is going to be very wary about the system at first, and they're going to want to do us to do all kinds of checks. We're really down for doing that, but eventually they're going to see that the system just works every single time.
Yeah, that's the intention.
Well, that's my hope, and I mean, I'm just going to keep working on refining the system. I'm just going to be working on that until I succeed or I die. And hopefully, actually, there's always the possibility that we will fix the death problem. I'm not sitting here saying that's going to happen, but it's a possibility that the death problem will be fixed. Go ahead.
Yeah, I mean, regarding FDA, I just want to say that there's actually ways around that. So, like, for example, there's this company called Minicircle that they are based in Prospera, some like economic zone in Honduras or something. And, well, they are not regulated by FDA because they're not in the US, but, you know, you can still buy their stuff. Actually work on genetic engineering, and they're doing, like, clinical trials of different gene therapies.
Atha, did you already dissolve the UK organization?
Yeah, I arranged for that already, because now we are just in the US, basically.
Yeah, but maybe that was a mistake. Maybe we should run both so that we can have... No? I thought that maybe... Go ahead.
Hang on.
Yeah.
I was told in no uncertain terms by... Yeah, I was told in no uncertain terms by our business advisors that it would be a mistake to retain multiple companies, mainly because they thought that that would make us look really shady. So, we do understand that there are different regulatory environments in different countries, but at the end of the day, we want our system to be available internationally. Yeah, we are incorporated into Delaware, and it's a very sort of internationally friendly place to put us, because it makes it easy to arrange things like investment and so on. When it comes to the regulations, the FDA and so forth, we'll cross that bridge when we come to it. If we need to set up another branch of our company in another country in order to actually proceed, then that's things we'll consider at the time, and we'll look at the pros and cons of that, including what it makes us look like, including what it does for the safety factor of what it is that the regulations themselves are actually trying to achieve. Because we don't want to make something that's unsafe just to spite the existence of regulations. We're not that kind of group.
Yeah,
we do have some standards.
The thing of companies like the one I mentioned is that they're setting a precedent, right? So if this company gains some reputation, it may no longer look shady to go to this country to escape regulations, because it becomes legitimate if they end up doing work and stuff. So anyway, I think there's a whole bunch of bio researchers that are actually thinking that FDA is way too what's the word? Not conservative, but anyway, way too risk averse. So this is becoming kind of a bit of a consensus in the research community. Yeah, well, not consensus quite yet, maybe, but it's very much a lot of people agree with that. So anyway, I think that there is good hope that there will be ways around the regulation when time comes. Yeah.
I need to go.
Well, we did say sometimes you have to take risks.
Go ahead. Let's let Tholin...
I need to go, but I would like to keep talking to the both of you, because it sounds like you need my help with ASIC stuff.
Yes, I wanted to... I don't know if you've both talked already, but...
We have to start with synthesis,
Like,
so then we'll move to ASIC.
Talk about silicon stuff, so... Talk more,
Tholin's aware of me.
Just one tip, if you want to put this on an ASIC, you need to drop VHDL. Open lane only does Verilog. Oh, I need to go immediately, so I will see you.
Alright, I will see about that.
Take care, Tholin, and thank you.
See you later. Alright, are we finished up here? I think we went way
unless
over
anybody
an
else
hour,
wants to talk.
45 minutes. Anybody else have any questions?
Officially finish the stream, just telling Carlos about that. But like, of course, anyone is welcome to like hang around and keep talking. So,
does anybody else have any questions? Because if not, we'll call it a day. And I'm glad you came. Thank you, everybody, for coming. This has been awesome. I'm glad we got a chance to talk about this, tell you where we are. And here's your final comments.
Yeah, I really look forward to what we can achieve. I think it'd be great to have you keep in touch if any of you want to be more involved. And we'll be putting this on YouTube, on our channel, and we'll hopefully be holding more events like these. So, thank you.
All right.